So, good morning, everyone. Welcome to the, as I told in my community post, welcome to the incredible crash course. And this is basically we are covering entire chemistry in a comprehensive and very structured way, in which I'm going to explain every topic in depth while maintaining a pace. If this is your first time visiting this chapter, I would recommend studying from somebody else who has dedicated more time to this topic, because this is one of the fundamental topics. But if you are revising this chapter, then this is going to be a fire session for you. And say if you have very less days left for the exam and you want to cover some basic concepts for you to move on to other chapters, then feel free to use this lecture to your own benefit. This is the first part of presumably two parts. In this lecture, I have covered the fundamentals, and in the next one, I will be covering the more quantum aspects of the structure of atom, accord, uh, along with the Bohr's model. So, let's start our journey. Cakes chem, chemistry the right way. Pronounce this as cakes. This is chem. So, what exactly is an atom? Do you want me to answer that? An atom is the fundamental unit of life. For example, you are made up of atoms. An atom is basically its nucleus. It's surrounded by electrons. Man, you have studied this shit in sixth class. Do you need me to remind you? But yeah, let's learn how to represent an atom. So, in a nucleus, basically there are both protons, and say this is a proton, this is neutron. There are a lot of those in a nucleus. A nucleus is the basically it's the center of the geometrical center of the atom, and a lot of protons and neutrons are there. Protons are positively charged, but neutrons have no charge. And say this is an atom, this is like the representation. For example, I can write it like uranium 92 238. This means the x here is u, and this is the mass number, and this is the atomic number. Now keep in mind that only for hydrogen the atomic number is equal to the mass number, but for every other element the atomic number is always less than the mass number. And why is that? Because the number of neutrons plus protons will always exceed the amount of protons, and then hydrogen is the only atom with no neutrons at all. So here the mass number is basically a collective measure of how many nucleons or neutrons plus protons are there, and the atomic number is a measure of how many protons are there in the nucleus. Or in order to maintain the neutrality in the neutral state, it is also equal to the number of electrons which are present in the atom. Okay, now you need to learn the special particles, especially alpha particle, proton and neutron, and beta particle as well. So take a look at these numbers. Alpha particle is basically it's a helium nuclei with a +2 charge, and it has a mass of 4 atomic mass units. You should know what this means. And a beta particle is basically it's nothing but a it's a fast moving electron, and it has a -1 charge. And see, its mass is basically 1 upon 1836 atomic mass units, and you can approximate 1836 as 6 into pi raised to the fifth power. This is, I don't know where it can be used, but maybe some calculation where you have to compare pi and something. Just keep this in mind. I know it has helped me in one question, but I don't remember which one. The positron, it's basically the anti-particle of a electron. It's the anti-particle of a electron. So basically it's just an electron with a positive charge. You don't have to study about this in detail. Ignore this guy. A proton, as I told you, it has a positive charge. It's a positively charged nucleus, and its mass is 1.0007 AMU, and a neutron is 1.008 AMU. Neutron, as I told you, is neutral. Okay. Now let's learn about isoseries. What is an isoseries? The word iso implies same. So if I'm saying iso something, means that that something is iso in one or more elements or entities means they have the same characteristic or statistic of something. So if I say that two entities are isotopes, that means that they have the same atomic number but different mass numbers. For example, in P block you will study there's another carbon isotope which is 14C6. But you can see they are all the same atomic number, but they vary in how many nucleons their nucleus holds, and specifically it is only the number of neutrons which varies, otherwise there would be charge imbalance between the isotopes. If we talk about isobars, isobars means that all those entities which have the same mass number but have different atomic number. For example, even argon 40 is there. So you can see they all have different atomic numbers but they have the same mass number. So this is called an isobar. If we talk about isotone, isotone is basically is the number of same number of neutrons. How do I calculate that? Well, you know that the upper number, the mass number is neutron plus proton. The lower number is just proton. So if I subtract the lower number from the upper number, I should get n, or the number of neutrons. So if you do 14 minus 6, you get 8 here. And if you do 16 minus 8, you get 8 here. So they have the same number of neutrons, these two entities, and hence they are called isotones. Use n to remember neutrons. If we talk about isodiapher, isodiapher is basically, you can say, entities with the same neutronic excess. What does this mean? This means that basically the difference between their number of n plus p minus p, like if you look at this using the n plus p definition, this is nothing but it's n plus p and z is just p. So if I do neutrons plus protons minus 2 times protons, this is n minus p, or you can define as it as neutronic excess, or how many more neutrons are compared as neutron are there as compared to the number of protons in the entity. So here you can see a minus 2z gives me 234 minus 180, and this is 238 minus 92, or you can say 238 minus 190, sorry, whatever. I don't do the math, just verify it yourself. But these two are isodiaphers and they have the same neutronic excess. Now if we talk about isoelectronic species, they are the species which have the same number of electrons. For example, this oxygen atom in its base state has 8 electrons, but if we add minus 2 charge, it now has 10 electrons. Similarly, 9 plus 1, fluorine with 1 extra gives 10. Neon in base state only has 10 electrons. Sodium has 11, but if you remove 1, it has 10, and same with magnesium here. And if two entities happen to have the same number of electrons while also having the same atomicity, they are called isoesters. For example, here you can see carbon dioxide and N2O. Carbon has, I think, 6 electrons. Oxygen, 2 moles of oxygen are going to have 16 electrons. Here nitrogen in total have 14 electrons and one oxygen has 8 electrons. So you can see 6 plus 16 is 14 plus 8. Both of them are equal to 22. So these are called isoesters, which have the same number of electrons and the same atomicity. Okay. Now this is a not important topic, so feel free to skip this. But if you want to learn about the old models, I am more than ready to help you. So if we talk about the J.J. Thomson model, the J.J. Thomson model was nothing but it was a J.J. Thomson thought that the atom was nothing but a positively charged sphere with negative electrons embedded into it. So here you can see that the definition I've written: uniform positive sphere with electrons embedded into it. This was what J.J. Thomson thought was an atom. This is also called the watermelon model and also the plum pudding model, because you can see it resembles a watermelon with its seeds inside, and plum pudding basically is the surface of a pudding and there's bits of plum. Plum is a fruit in it, so this is called watermelon or plum pudding model. What were the drawbacks of J.J. Thomson model? Like, why did we decline this model's existence? Well, it's because it could not explain the stability of the atom. It could not explain why the electrons were static, like fixed in one place. And It could not explain the results of the alpha particle scattering experiment, which we'll know on the next slide. Okay, so this was the J.J. Thomson model. If we talk about the Rutherford model, we are also going to learn about the alpha particle scattering experiment here, which was basically this was a source of alpha particles. Remember, 5 slides ago we stated that alpha particle is nothing but it's the helium nuclei with a positive 2 charge, and basically if this alpha particle passes through the gold foil. Now keep in mind that the gold foil used in this experiment was extremely thin, like 1000 atoms thick. And if you know the dimensions of an atom, that is an incredibly thin value. And if this alpha particle happened to pass through these 1000 atom thick sheet, what do you think should have happened? If J.J. Thomson's model was true, then this should have been like filled. It should have been very rigid, and there should almost be no spaces between the individual atoms. So all the alpha particles should bounce back basically. On Academy, don't sue me, but it should bounce back, and that is far from what happened. It turns out that most of the alpha particles just phased through the entire 1000 atom sheet like nothing happened. How? Well, that's because J.J. Thomson's model was wrong. In an atom, most of the space, like this space, just so happens to be completely empty. And it is very easy for the helium nucleus to pass through this empty space. Let's look at the diagram. Beam of alpha particles, you can see most of them just pass unfazed, but very few of them do get deflected. You can see very some of them are getting deflected, and that is because they are unlucky enough to ignore the free space and instead strike the nucleus in the center, and hence they get deflected. Okay, now if we talk about the actual observations of what Rutherford saw, it was basically mass of each gold, yeah, as I told you, mass of each gold atom should have been spread evenly over the entire atom, and alpha particles should have had enough energy to pass directly, but they did not. I mean, they did, but it was observed that most of them passed through undeflected. Okay, as I told you, most of them passed through the sheet undeflected. A very small number of them were deflected by small angles, and even fewer of them, like 1 in 20,000 alpha particles, bounced back completely on near 180-degree angle. Like few of them were unlucky enough to strike the nucleus straight head on and then move back along the same way. So this tells us that the most of these, let's read the NCERT only. What conclusions can we deduce from the Rutherford model? Well, most of the space in atom is empty. Only a few of them were deflected, so deflection must be due to enormous repulsive force. Like helium nuclei, of course, is positively charged, and the nuclei of gold is also positively charged. So this repulsion must have caused the helium nuclei to deter away from the path where it was going to strike the nucleus, and hence this deflection is explained. And the positive charge of the atom is not spread throughout the atom as Thomson had presumed. It's the same thing as earlier, because this deflection was only there when you were close to the nucleus. Otherwise, there was no deflection at all. Hence, there was no positive charge here and no repulsion. And this very obvious consequence of this, volume occupied by nucleus, like here you saw very small amount were deflected 180 degrees, so the volume occupied by the nucleus is negligibly small compared to the total volume of the atom. The radius of the atom is about 10 raised to power minus 10 meter or 1 angstrom, whereas that of the nucleus is 10 raised to power minus 15 meter or 1 Fermi. Okay, on the basis of above observations, positive charge and most of the mass were densely concentrated in extremely small region in the center, and this small portion is what we refer to as the nucleus of an atom. And this, although this model had failed due to reasons we are going to study later, many postulates from this model are still in use today. For example, this nucleus part, that nucleus does exist. And according to him, the nucleus was nothing but it was surrounded by electrons that move around the nucleus in very high speed in circular paths called orbits. And according to him, the model of atom resembled the solar system, where this is the sun and these are the planets. And they are held together by electrostatic forces of attraction. Now, why did this model fail? Well, in EM waves in physics, you should have studied. I don't know if you have, but you should have that any accelerated charge is capable of sending out waves. Waves, in the sense, accelerated charge can send out electric and magnetic fields which are perpendicular to each other, and this is a wave, electromagnetic wave. And these regenerate each other, so it goes on for very long periods of time and distance. So, of course, this consumes energy. So, how is the orbit stable? I mean, if you have more energy to give out, you cannot be stable, right? Because energy, the lower your energy, the more stable you are. But if you're still giving out energy in the first place, how are you at your most stable state? And as you know, nature has this tendency to drive its members to stability. So, how is this possible? And it said nothing about the configuration of the atom. Like, you know how we studied the groups of the periodic table, it said nothing about that. So that was a major drawback because we could not explain that aspect of the periodic table and atoms in general. And it failed to explain spectrum, which we are going to read later. And this is an important dependencies you'll have to see. Just look at it once. These are the number of particles which are deflected at an angle theta. Like, if I want to know how many particles deflected at this angle, at this angle, so I can input that angle, and the dependencies are it is directly proportional to the square of the atomic number. It is directly proportional to the thickness of the foil which you are using, and it is inversely proportional to the square of the kinetic energy, or the fourth power of the absolute speed of the approaching particle, and it is also inversely proportional to the fourth power of the half angle sine, which means sine theta by 2 raised to the fourth power is inversely proportional to the number of particles which are scattered by theta. Okay, so that was it. So what model do I use? JJ was wrong. Rutherford was wrong. So what model do I use to describe atoms? Well, before we move on to the next model, we need to know a few things. What things? Wave characteristics. You should know this, and if you don't, shame on you. But I'm going to give a small revision. This is a wave. A wave is a disturbance which travels like this. For now, you don't need to know about longitudinal waves. Just think this is a wave, and basically, the lower part of the wave, like where it is below the axis you are considering, is called a trough. And if it is above, it's called crest. Quite evidently, its disturbance in the both positive and negative direction is the same, and it's called the amplitude of the wave. And this is called the wave height. And this is the direction of propagation or direction of travel. Now, what is frequency of the wave? Before that, let me tell you about wavelength. Wavelength is the distance between two consecutive crests or two consecutive troughs, or the total length covered by one crest plus one trough. So, this series of crests and troughs, how many of them are passing through a point in 1 second, is called the frequency, and it is the inverse of the time period of the wave. The wave number is number of wavelengths per unit length, and it is nothing but the inverse of the wavelength, as I have written here. And this is the most fundamental and useful relationship which you are going to use in this chapter, is that this product of the wavelength and frequency is always equal to the speed of light in vacuum, which is 3 into 10 raised to the 8th power. And this is true for any electromagnetic wave. What is an electromagnetic wave? As we learned earlier, electromagnetic waves are waves which are produced by charged particles which are undergoing acceleration. Basically, how this happens is that Charged particles undergoing acceleration provides an electric field, and time varying electric field causes an magnetic field to appear, and they just so happen to regenerate each other via Faraday's laws. And this goes on like for a very long time along a single direction. So basically, and this travels with the speed of light. So the cross product of electricity, what I was saying, cross product of electric field and the magnetic field is equal to the speed of light. And this cross product relationship also shows you that these three quantities are mutually perpendicular to each other, and both the electric field and the magnetic field vector have the same speed, same frequency, same wavelength, and same amplitude. So this is called an electromagnetic wave. As the name suggests, electromagnetic wave. Now these waves do not need a medium to travel. And hence we are able to use radio and stuff because those are also electromagnetic waves. And electromagnetic waves of different frequencies. Like if I vary this frequency at different values, I can make a spectrum. Keep in mind, this is not the spectrum I'm mentioning here. This is a different spectrum. It is basically a collection of electromagnetic waves of different frequencies and what colors or in what region they lie in. Okay, so the visible spectrum lies in between the ultraviolet and the infrared region, and this is the colors of the rainbow, as you can see. Webb, Gear, you learned this in childhood. And see, this wave interpretation of electromagnetic waves or light in general, it could explain the phenomena of diffraction and interference. Diffraction is nothing but, as you know, light passes through a thin obstacle, so it scatters around the obstacle like this. It appears to be bouncing off the edges of the obstacle. And interference is basically the constructive interference of two wave fronts like this to form points where bright fringes are obtained. You know, need to know a little bit of wave optics for this. If you don't, just skip this part. There are bright fringes and also dark fringes are obtained. So this could be explained by considering light as a wave, but it was unable to explain the phenomena of black body radiation, photoelectric effect, and the heat capacity of solids as a function of temperature. What is heat capacity? This is heat capacity. Like it is the it is a quantitative measure of how much a body's temperature would change when supplied with a certain amount of heat. So that heat in joules is equal to the heat capacity into the change of temperature in Kelvin or Celsius. So this heat capacity is a function of the nature of the material, but in some solids this just so happens to be a function of the temperature itself. So why it happens is unable to be explained while considering light as an electromagnetic wave. And lastly, line spectra of hydrogen like species, which I will tell you later. Now let's learn about blackbody radiation. What is blackbody radiation? First, let's learn about some basic heat transfer mechanics. When an object is irradiated with light, like if I take an object and I put light on it, a part of this energy, this light energy, is reflected, and one part of it is absorbed, and another is transmitted after absorption. So, reflected, absorbed, and transmitted. That. So, ordinary objects, for example, a pen or a book, they are imperfect absorbers of radiation because in nature nothing is ideal. But if we talk about a hypothetical ideal body which emit and absorb radiations of all frequencies uniformly, like whatever you throw at it, it's going to throw back. It's called a black body. And it is going to be a perfect emitter and absorber. Carbon black is a good approximation to a black body. And a good physical approximation is a black body. You don't need to know this. But keep in mind, carbon black is a good approximation of black body. So, a black body is also a perfect radiator of radiant energy. Furthermore, a black body is in thermal equilibrium with its surroundings. These are general points which can be asked to you via MCQs, and hence I picked them at from the NCRT. So it radiates same amount of energy per unit area as it absorbs from surrounding in any given time. You will get to know later that energy per unit area, this has to do something with something called intensity. But yeah, we'll look at it later. Now something interesting we saw here, that the amount of light emitted from a black body depends only on its temperature. And amount of light is basically another word for the intensity. It only depended on the temperature. Like this, the intensity dependent was dependent on the temperature. You can say it has different values at temperature. And when you took the wavelength and when you started decreasing the wavelength of the light incident on the black body, the intensity started to increase. Like here you can see, read this graph from right to left, opposite direction. When I started increasing the wavelength, decreasing the wavelength, the intensity started increasing, and this happens at both the temperatures. So according to the wave theory of light, light is a continuous wave of energy, and for the wave, energy is proportional to its intensity, proportional to its brightness, and inversely proportional to its wavelength. So if I heat an object, the intensity should keep on increasing forever till infinity. But the graph isn't strictly increasing or decreasing. It peaks at a certain value, certain maxima, and then it starts to fall rapidly. Why? This effect was not explained by the wave theory. If wave theory puts forward a certain postulate and that postulate fails to explain a certain phenomena, then we can say that there is some mistake in applying the wave theory as it is here. So, what else could we do? Hence, maybe this is an exception. Let's try applying it on the photoelectric effect. What is photoelectric effect? It is ejection of electrons from metal surface. You are going to study this in much detail in physics, but for now, we only need to know that if we apply wave theory here, then according to wave theory, even dim light should have enough energy to give to an electron to soak up that energy and release itself from the metal surface. And maybe the light is dim, intensity is low, but maybe if I put it for very long periods of time, I will give enough energy so the electron can soak it up like a sponge and release from the metal surface. But turns out no, that does not happen. Hence another exception to the wave theory here. Why is this happening? In reality, it seems there is no time lag. Like however dim the light may be, its intensity does not seem to affect the emission of electrons at all. This goes directly against what we studied in wave theory. You need a certain energy to remove electrons from the metal surface, and increasing or decreasing the intensity does not give you any kind of alteration or control over that energy, and that means wave theory is incorrect. Or rather than saying incorrect, we can say that it is not fully applicable here. Now, all of these experiments suggested that energy is not continuous. Instead, it's a discrete smallest value. A good way to understand this is that instead of going up and down like a continuous value like this, like I can take any here. No, it does not work like that. It's like maybe say you have a ball in a pit. Okay, it's not like you can just roll it over and get it out of the pit. It's like you have small steps in the pit here. The ball can be stable and can rest here. It can rest here, 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 but it cannot rest at any of the intermediate values. So this distance, or the basically the discretion, this is discretion. Discretion is basically a fixed interval where possible stable values of energy are possible. So that is called discretion, and this discretion in quantum mechanics or in this chapter is what we call a quantum. We are going to learn about the Planck quantum theory later, but first I asked Gemini to write a good write-up. So read this if you want. This is going to help you understand the topic. Oh, so read this. Now let's move on to Planck's quantum theory. Planck assumed that radiation could be subdivided into discrete chunks of energy. That's what I told you earlier. that if I am putting this radiation in the black body, it can be broken into discrete chunks of energy, which we call the quantum. And he suggested that atoms and molecules could emit or absorb these energies only in discrete quantities. Discrete again in steps, not in like a continuous fashion, and not in a continuous manner. He gave the name quantum to the smallest quantity of energy that can be emitted or absorbed in the form of electromagnetic radiation. So basically, in physical standard, you can call this basically the height of each step. He provided the name quantum to the height of each step which can be traversed and used to move on to the next step of energy. And for the photon or the particle of light, he said that the energy is proportional to its frequency instead of its intensity, independent of the intensity, and hence E is equal to h nu, where h is the Planck's constant with a value of 6.63 into 10 raised to power negative 34, or can be approximated as you can call it 20 upon 3 into 10 raised to power negative 34. You can also use this approximation for gravitational constant G in physics. Okay. Credits to Physics Galaxy for this paragraph. Radiant energy is emitted or absorbed discontinuously, same as the discrete written here, discrete in manner, and form of small energy packets called quantum or photon if you are dealing with light. Energy of one photon is equal to h nu, and total energy is quantized. Like this means that total energy is going to be an integral multiple of the energy of a single photon. It's like saying that if I have a staircase which is leading to a terrace and each staircase height is h, so the height of the terrace is going to be an integral multiple of height of each staircase. Okay. And if I take 1 mole of photons, which is 6.023 into 10 raised to power 23 photons, then the energy of 1 mole of photons is going to be the energy of 1 photon into the Avogadro number, and that this number is what we call Einstein energy. Okay. According to Planck's quantum theory, the energy is directly proportional to frequency and not the intensity of the light wave. And intensity in particle physics is termed as number of photons per second. Looks like I have solved the case. But no, something bad happens. Wave nature could explain diffraction and interference but failed to explain black body radiation and photoelectric effect. But the particle nature or Planck's quantum theory could explain the photoelectric effect and the black body radiation, but it failed to explain interference and diffraction. What is happening, and how is light able to show all four of these properties at once when it has been confirmed that it is neither wave nor particle? Well, turns out it is both wave and particle. But it is hard to visualize or understand any of this now, and hence you will have to refer to the next lecture, before which you will have to learn about some more topics. Let's look at atomic spectra. Credits to Khan Academy for this photo. Well, if you have an electron in any certain shell, and if you happen to provide energy to that electron, it can, depending on how much energy you provided, it can jump from its current state to another state, another orbit, and this orbit is what we call the excited state. Say in ground state, an electron is at level 1 and it goes to second level on excitation or on the providing of energy. So the second orbit in which the electron now is roaming around is what we call the first excited state. It's like in open organ pipe you used to know nth harmonic is n plus 1 n plus 1th harmonic is nth overtone, something like that. And here you can see this is the first excited state. For the first excited state, the value of n is 2, where we will learn what n is. But similarly, for the second excited state, value of n is 3. N is basically just the number of orbit. This is third orbit, which just so happens to be the second excited state. And this is true for any orbit, okay? And the for ground state is the ground state. It's not excited. It's the unexcited state, okay? So let's read theory which I have written. The electrons get excited on adding energy to them, as I told you, but in their higher orbits they happen to be very unstable, so they jump back to their stable place, and while doing so they give back the energy which was provided to them in the first place. And this energy which is released, it is released in the form of photon or the quantum of light, okay, releasing a photon corresponding to the energy which you had given to the electron, causing the jump in the first place, okay. So when it jumps down, it releases a photon, and many times this photon just so happens to be in the, now photon is there, it will have a wavelength. So this photon sometimes just so happens to be in the range of the visible spectrum, and hence this causes color to appear. That's interesting. And this color is basically, if we solve it on a photographic plate is basically, it can cover all these colors in a single plate, like show us which colors were obtained. This branch of chemistry or physics is called spectroscopy, and a unique thing is that this spectrum is unique for every element. It's like a signature of the element. And for example, if we heat H2 gas, the wavelength released, if we solve it using a prism or a spectrographic plate, it breaks down into all the colors which were corresponding to the energy differences. Like in a single H molecule, on providing energy, you cannot decide how much energy is given to which electron. And there are multiple atoms here, so multiple transitions take place. So this transition is also there, also there, also there. Every possible transition takes place, and this a net wavelength is released, which on passing through a prism or prisming, it breaks into all colors which are corresponding to all the energy differences which were absorbed by the electrons. Like all of these give a distinct color or may not give color at all, but all of those who give color are received on the plate, and hence this unique signature for every element is obtained. This is the signature for hydrogen. And say if we are receiving, this is a light source, and we are receiving light from the light source and resolving it on a spectrographic plate, and this is the spectrum we obtain, we can safely say that a light source has hydrogen, because we have to use our knowledge of atomic spectra as a dictionary. You need not remember this, but higher level, college level chemistry students must know this, and this is the signature or the atomic spectra of hydrogen. What is emission spectrum? Basically, it's the same thing as earlier, but I'll tell you something amazing. Spectral analysis. Say we have a sample light source which has both hydrogen and helium in it, and it gives us light. Okay, and this light we receive it on a spectrographic plate, and this is the spectrum we obtain. And we see that it coincides with the spectrum of hydrogen, but it also coincides, like the dimmer lines coincide with the spectrum of helium. This means both helium and hydrogen are present in the sample, and since the lines of helium are dimmer as compared to the hydrogen ones, this simply implies that the concentration or abundance of hydrogen is more than that of helium in the sample itself. And this is basically, this is called emission spectrum, where we make the source emit some kind of radiation, and receiving that radiation, we tell about the components of the sample itself. Okay, now let's learn about absorption spectrum. What is absorption spectrum? It is the photographic negative of a emission spectrum. And how is it obtained? Basically, here we use the emitting property of the source to get information about its component or its concentration or relative abundance of its constituents. But in absorption spectrum, the sample is going to be our victim. Like we are going to radiate it using forms of energy, be it temperature, be it light, whatever. A continuum, for example, white light. Continuum is basically, you know, rainbow is comprised of white light. Sorry, the components of white light is used in rainbow. So this continuum is basically a, you know, band of colors which all blend into each other so nicely. So this continuum, if we pass it through the sample, so you know this sample is, it absorbs specific transitions, specific amounts of energy it absorbs and then gives out. Now this giving out of the atom can be in any direction, okay, and most probably it is going to be a random direction which is going to be completely different from which direction you radiated the sample from. So these lines just happen to go missing. The lines which used to correspond to a transition in the atom itself, they go missing because they are now sent away in a direction which is unbeknownst to the relevant direction, and hence these lines are disappearing and the original continuum is obtained. Like imagine a rainbow, we put in that continuum only, and these lines disappeared, which means these lines are basically again a signature for the atom. And the cool part is it is a photographic negative of the emission spectrum. Think of it intuitively, it's really easy to understand. Like here, ignore this, I accidentally added this one, but yeah, you can see these coincide, these they all coincide. It's the photographic negative of the line spectrum, because here we analyzed the emitted rays and hence we only got the rays which were emitted. But when we analyzed the absorbed rays, we got only the rays which weren't absorbed. I hope this is easy to understand for you. And if we talk about the last topic of today, which is the line spectrum of hydrogen atom, learn this golden formula. The inverse of the wavelength, which is equal to the wave number, is equal to the Rydberg's constant into 1 over n1 square minus 1 over n2 square into the atomic number squared. What does this even mean? Well, this means that, say, from a transition is happening from a higher level, say n2, n is the principal quantum number, and say to n1, okay. So that formula is nothing but it's a measure of the wavelength which is released when this transition occurs. So this is going to release a photon as we discussed, and this wavelength, the wavelength of the photon which is released, is given by this formula, okay. And here we are using a constant in multiplication which is called the Rydberg's constant, and its value is 1.0967 into 10 raised to the 7th power, safely approximated as 1.1. And I would suggest you to remember the inverse of this constant as well, because you know they ask you wavelength, okay. So the formula is for 1 by wavelength. So many times you have to do the reciprocal of a quantity which contains the Rydberg's constant in the numerator, and hence the Rydberg's constant comes in the denominator. So just remember this value. It is 9.12 or 9.11 into 10 raised to the power negative 8, okay. Remember it. And some technical terms you must know. If the exam asks you the first line, it means the transition from the completely like adjacent orbit, like the first transition, first possible transition, okay. That is what you call the first line from n plus 1 to n. And this is also the shortest energy difference. Quite obviously this is the like shortest energy difference possible, and you know the energy is inversely proportional to lambda. The exact formula is E is equal to hc by lambda, but we will look into it later in the next lecture. So the shortest energy difference automatically implies the existence of longest wavelength. And the last line, as evident, means transition from infinity to a certain orbit. And this is going to be the shortest lambda and the longest and or largest energy difference. Okay, now what is this? This is basically we are describing the if the our it is going to jump from a higher state to a lower state. So we categorize all the transitions which happen to a certain lower state. For example, if 2 to 1 happens or 3 to 1 happens, 4 to 1 happens, we categorize them as one single group. Okay, and these groups have names because their wavelengths lie extremely close to each other. Okay, so it just so happens that if our victim group or our lower state is the first state or the ground state, then the series or group is called Lyman series, and the spectral region in which the wavelengths where Lyman series is used is there, it's in the ultraviolet region. The Balmer series is in the visible region. More specifically, the first four Balmer series are visible. For example, this means that 3 to 2 is visible, 4 to 2 is visible, 5 to 2 is visible, and 6 to 2 is visible. For it to be visible means that these transitions give us a color which can be observed by the naked human eye. If the lower state is the third state, then it's Paschen series, the fourth is bracket series, and the fifth is P-Fund series. Just for your knowledge, if the lower state is the sixth state, it's called the Humphrey series. Okay. And the number of lines from a certain above state, like higher state n2, to a lower state n1. If we want to calculate the number of possible lines, like this number of possible lines from a certain state to another state, the number of possible lines is, let me help you visualize it. For example, say if I do n is equal to 6 to n is equal to 2. So a direct transition must be from 6 to 2 direct. But maybe another transition happens from first 6 to 4th and then 4th to 2nd, but then 6 to 5th and this. Then maybe it's broken down into multiple ones like this, where every step is taken cautiously with only one interval in between, and say 1 to direct 3 and then 3 to 4. So this is basically, it's a lot of permutation and combination to find the number of total spectral lines possible from a certain higher state, in this case n is equal to 6, to a certain lower state, which in this case is n is equal to 2. So if you want to calculate the total number of spectral lines possible, the formula is n2 minus n1 into n2 minus n1 plus 1. And if n1 just so happens to be the ground state, this formula reduces to n minus 1 into n by 2. And this is a more standard formula and it's more used in your JEE or NEET examinations. And that was it for this lecture. What's real? Both theories are true, where light is both wave and particle, which we'll cover in the next lecture. And that was it for structure of atom part 1. We have covered everything essential and I have built your concepts from the ground to a respectable level. And in the next lecture, we will be covering Bohr's model and the quantum aspects of structure of atom. This is the incredible crash course, and please leave a like if you like the video, subscribe and share. We are almost at 1000 subscribers. And that's it. Thank you for your attention.